A particle is launched at an angle of theta with a velocity of 16 meters per second. At what angle should the particle be launched if it is to hit a target 22.6 meters away? Give your answers correct to the nearest degree. Okay, if we draw a little sketch of the situation, so we're going to launch a projectile with an initial velocity of 16 meters per second, and we're going to require the range to be 22.6 meters. Writing down the position vector, so for the horizontal component, that's just going to be the initial velocity, so it's u cos theta, cos times time, there's no acceleration in the horizontal component, and then using ut plus a half at squared for the vertical components, the initial velocity would be u sine theta times t minus a half gt squared. Putting the numbers in, we've got g acting downwards. Put the numbers in, we've got 16t cos theta, and then 16t sine theta minus 4.9 t squared. And what we've got to find is t given the information. So if we write down that the x component will be 16t cos theta, call that equation 1, and that y will be 16t sine theta minus 4.9 t squared, call that equation 2. Now you could eliminate t from question form 1 and then substitute it in there, but it does become a bit harder. If you eliminate it from here, you say the following: from 2, we put 16t sine theta minus 4.9 t squared is equal to 0, because at the maximum range, the vertical component of displacement is 0. Now, if we factorise out, we get t 16 sine theta minus 4.9 t is equal to 0. Now, we can ignore this one, because this is the time where it started from, the initial position. So then we can say then 16 sine theta minus 4.9 t is equal to 0. Now we can make t the subject, so 16 sine theta is equal to 4.9 t. These are just the initial equations, but from the last part, 16 sine theta is equal to 4.9 t, will give that t is 16 sine theta over 4.9. Now what we're going to do is put that into here. So substitute into equation 1. We're going to have 16 times t, which is now 16 sine theta over 4.9. Don't forget the cos. 16 times 16 gives 256 sine theta cos theta over 4.9. Now we want the range to be 22.6, so we need to put that equal to 22.6, the horizontal component. And using that sine 2 theta is equal to 2 sine theta cos theta, that means we'll do 4.9 times 22.6, take half of 256 because it's 2 sine theta cos theta, which is 128 sine 2 theta. And then sine 2 theta will be 4.9 times 22.6 over 128. Now to solve that, so sine 2 theta is equal to 4.9 times 22.6 over 128. Use the fraction button on your calculator, just put that in, and remember the angle needs to be between 0 and 90, so therefore for 2 theta, the angle will have to be, 2 theta will have to look for angles between 0 and 180. So that will give you, when you work this out on your calculator, you get 5,537 over 6,400, exactly on your calculator. Do sine to the minus 1 of that, that will give you 59.9 degrees. We do the South Asian Tennis Club, or whatever you remember this as. We want to know where this is positive. So sine is positive in the first and second quadrant, so we draw an angle with the x-axis, 59.9 here and 59.9 here. So starting here, we only have to go up to 180, so it's going to give that 2 theta had to be 59.9, or 180 minus 59.9, so that's 180 minus that angle, which gives 59.9 or 120.1. Then if we divide by 2, we're going to get 29.95 or 60.05. We have to give the answer to the nearest degree, so it's 30 or 60, correct to the nearest degree. Now we can look at this using this GeoGebra app, which I will put in the notes of the video. So here we've got an initial angle. Here we've got an initial angle of 30 degrees, so 30 degrees here, and the initial velocity is 16. Okay, and we can see there we get a range of 22.6. Now, if we change this to 60, which is the other angle we calculated, look what happens. Okay, we'll get the same range, but the particle will go higher. And we'll still get a range of 22.6. And for any other value, so 30 will go up to 30. So if we went to, let's say, 20 degrees, okay, so we've got a range of 16.99, and then went to 90 minus 20. We've got 16.77, whoops, moved it. 16.77, and down to 20, you can see we get 16.77. So for any angle, we're always going to have two angles which will give you the same range, except when theta is equal to 45. If you look at the motion here, 45, that is the maximum range that we can actually get, and that's because sine 2 theta gives sine of 90, and sine of 90 is 1, so that's the maximum that sine can be. And see, 45 is the maximum, and then for all others we get two angles. So if we just look at 60, and with this app as well, you can do an animation. You can see the vector and the horizontal and vertical components of velocity. If we click here, we can also see the displacement vector. Yep, that's 59. Let's move it to 60. Okay, you can reset using this and start it again. Stop it anywhere you want, start it. So it's quite a useful little app there to visualize what's going on with projectile motion. Okay, so this has been a video to help you find the possible angles you can launch a projectile for a given range. I hope you've understood, and I thank you very much for watching, and I'll remind you the GeoGebra app will be in the notes of the video.